Hi, David Ken here with another question in thermal concepts. In this question, we're looking at heating and cooling of different objects. We have a block of copper with a mass of 3 kilograms and a temperature of 90 degrees Celsius. We transfer it into a calorimeter containing 2 kilograms of water at 20 degrees Celsius, and the calorimeter itself is made of 210 grams of copper. So first let's draw a diagram of what's happening here. We have a container. That's what containers look like, right? It's full of water. The water and the container are each at 20 degrees Celsius. There's 2 kilograms of water and 0.21 kilograms of copper in the cup. And what we're going to do is we're going to drop a block of 3 kilograms of copper into the water. And this 3 kilogram block is at 90 degrees Celsius. And what we want to know is what the final temperature of this water and the whole system is going to be once they all reach thermal equilibrium. So there's going to be energy transferred. Energy is going to be leaving the copper block and entering the water in the calorimeter. But if we assume that no energy leaves the system, then we can say that the sum of all the energies transferred must be 0. We should be able to say that the change in the thermal energy of the block plus the change in the thermal energy of the water plus the change in the thermal energy of the calorimeter should add up to 0. Now, to solve this is because this one's going down, the energy in the block is going down, and these two are going up. Now, to solve this, we'll use the relationship Q equals mc delta T. We have the mass of the block, the specific heat capacity of the block, and the change in temperature of the block, plus the mass of the water, the specific heat capacity of the water, and the change in temperature of the water, and the mass of the cup, specific heat capacity of the cup, and the change in temperature of the cup. All of that should add up to 0. Let's grab that, move it down here a little bit so we have a little bit more room to work, because this is going to get to be a very wide equation. We'll start with the mass of the block, that's 3 kilograms. And the specific heat capacity of the block we have to read out of this table. For copper, it's 3.85 times 10 to the second joules per kilogram per Kelvin. Now don't worry that we have a unit mismatch here, Kelvin and Celsius, because a change in a Kelvin is the same as a change in a degree Celsius. So we don't need to do any conversions there. We get 3.85 times 10 to the 2 times the change in temperature of the block, which is its final temperature, which is what we want to know, take away its initial temperature, which is 90 degrees Celsius. Next, for the water, we have the mass of the water, 2 kilograms, times the specific heat capacity of the water, 4.18 times 10 to the third, times the change in temperature of the water. Now we don't know the final temperature of the water, but we do know the initial temperature of the water. And this final temperature of the water is the same as the final temperature of the block, because once the system reaches thermal equilibrium, everything, the block, the water, and the cup, are going to be at the same final temperature. It's going to be the same case for the calorimeter cup. We have the mass of the cup times the specific heat capacity of the cup, which is also made of copper, so that's 3.85 times 10 to the second. And then we have the change in temperature of the cup, which would be its final temperature, take its initial temperature. All of that has to add up to 0. All right, next up we have to expand some brackets. We have to multiply all of this into TF and into 90, all of this into TF and into 20, all of this into TF and into 20. So when we multiply 3 times 3.85 times 10 to the second times TF, we get 1 0.15 times 10 to the third TF. And when we multiply 3 times 3.85 times 10 to the second times negative 90, we get negative 1.04 times 10 to the fifth. Next up, we'll expand these brackets, and we get 8.36 times 10 to the third TF. And we'll multiply all of this times negative 20, and we'll get negative 1.67 times 10 to the fifth. Next up, our last block here. We'll multiply 0.12 times 3.85 times 10 to the second times TF, and we'll get 8.08 times 10 to the first TF. And all of that times negative 20 gives us negative 1.61 times 10 to the third. All of that equals 0. That's a huge line, but it's made up of only a couple of things. Terms of TF and constant terms. So we'll collect like terms. Everything with a TF in it, I'll add up together, and I'll get 9.59 times 10 to the third TF. And I'll add up everything that's a constant term and add it to the other side of the equation to make it positive. And that winds up being 2.72 times 10 to the fifth. Now it's a simple matter of dividing 2.72 times 10 to the fifth by 9.59 times 10 to the third, and we get that the final temperature is 28.4 degrees Celsius. Which doesn't sound like a big change, but it is in the range that we expect. We expect the temperature of the water to rise and the temperature of the block to fall. So we expect the temperature to be between 20 and 90 degrees Celsius. It's closer to 20 than 90 though, like it's not anywhere near the middle. But that's actually also to be expected, because if we go back to this table, we see that the specific heat capacity of water is 10 times more than the specific heat capacity of copper, which means that the copper needs to give up 10 times as much energy into the water to raise the water's temperature by the same amount. So a big change in temperature in the copper is going to lead to a small change in energy in the water.